In the 20th century, rockets carried human beings beyond Earth for the first time. We stood on the surface of the moon. We sent robotic explorers to every planet in the solar system. In that moment, the idea of living on other worlds no longer belonged solely to imagination. It felt tangible, like a future already opening its door. And yet, decades later, that momentum has slowed. We have not returned to the moon for half a century, and Mars remains stubbornly remote. Every serious attempt to establish a permanent human presence beyond Earth collides with obstacles that feel less like temporary delays and more like hard limits. It raises an unsettling question. What if humanity never truly leaves Earth behind? What if becoming a spacefaring species is not an inevitable destiny, but a beautiful illusion? And why do we so often confuse rocketry with freedom? When people picture rockets, they imagine freedom itself. A slender machine rising skyward, fire pouring from beneath, lifting human lives away from the ground toward a new world. The countdown reaches zero, engines ignite, and the vehicle appears to tear itself loose from the planet. In a matter of seconds, it seems to slip from Earth's grasp. This image convinces many that rockets are simple instruments of escape, swift tickets to anywhere beyond the sky. But the reality is far more complex. Rockets are not symbols of effortless departure. They are machines built to fight the most powerful force we experience in everyday life, Earth's gravity. And they do so at an extraordinary cost, one that is rarely acknowledged. From early science fiction to modern cinema, rockets are often portrayed as almost magical. A hero needs to leave Earth, the ship waits on the launch pad, and within minutes it reaches orbit. Entire months, sometimes years, of preparation are compressed into a single dramatic ascent. The engines thunder, the camera trembles, and soon the characters float weightless. Missing from these stories are the immense volumes of fuel required, the meticulous calculations of trajectory, and the impossibly narrow margin between success and disaster. Film and television polish away the difficulties, leaving the impression that leaving Earth is no more complicated than boarding a long journey train. We are familiar with airplanes. We step aboard, sit comfortably, and hours later, arrive on the other side of the planet. In our collective imagination, the jump from airplane to rocket feels like a natural extension of the same idea. If an aircraft can cross oceans, then surely a rocket can cross space. But the two could not be more different. An airplane moves through air, supported by wings and powered by engines that draw oxygen directly from the atmosphere. A rocket must carry every molecule of oxygen it needs, along with its fuel, and burn both at a ferocious rate, simply to rise against the planet's pull. To remain in orbit, a spacecraft must reach a speed greater than 28,000 kilometers per hour. This speed is not optional. Anything less, and the vehicle will fall back, returning violently to the Earth it tried to escape. The price of reaching that velocity is staggering. Modern rockets, whether launching satellites or astronauts, carry hundreds of tons of propellant. What we see standing on the launch pad is mostly fuel. The spacecraft itself, the part that survives and continues into orbit, is only a small fraction of the total mass. Around 90% or more of a rocket's launch weight is fuel. As it climbs, the rocket sheds itself in stages, discarding empty tanks to reduce weight, all so that a small remnant can continue onward. What appears to be freedom is, in truth, a vast and precisely timed act of sacrifice, where most of the vehicle is abandoned in the struggle to escape gravity's grip. During the space race of the 1,960 seconds, rockets became powerful symbols of possibility. They stood for progress, strength, and hope. Images of Apollo launches filled living rooms across the world, full of flame, thunder, and triumph. Rarely seen were the years of failure that preceded them, the shattered prototypes, the lives lost in training, and the endless calculations completed before a single launch was attempted. The public saw the victories, and those victories shaped the belief that rockets offered clean and direct paths to the stars. The untidy reality remained hidden. That simplification continues today. Private companies stream launches with elegant visuals and celebratory language. They speak of futures where rockets carry people between cities or onward to Mars, as though it is merely a question of patience before tickets appear. The deeper challenges, engineering reliability, human safety, and immense resource demands, are often confined to the margins. This is not deception so much as marketing. Spectacle sells, and few sights are as arresting as a rocket climbing into the sky. The danger lies in repetition. Over time, these simplified images build a shared memory in which rockets mean easy departure, where leaving Earth seems no more complicated than reversing out of a driveway. But to leave Earth is to confront one of nature's most unyielding barriers, gravity itself. Gravity anchors the oceans, holds the atmosphere in place, and governs the motion of the moon. Escaping it demands not only raw power, but exquisite precision. A rocket cannot simply rise straight upward forever. If it did, fuel would run out and it would fall back. Instead, it must curve sideways, steadily accelerating until it moves so fast that the curvature of Earth drops away beneath it. In this sense, orbit is not an escape at all, but a continuous fall around the planet. To remain in orbit, a rocket must achieve an exact balance between altitude and velocity. Every launch represents the combined work of thousands of people, years of dedication, and billions of dollars. What appears to be freedom from Earth is, in reality, the most restrictive and demanding form of travel humanity has ever attempted. Popular culture smooths away this struggle, because stories are simpler when machines function perfectly, when heroes reach space without confronting the true weight of what it takes to get there. Yet, behind every graceful image of ascent lies an unseen mountain of effort. We want to believe the sky is open, that we are only a few steps away from escaping the troubles of Earth. Rockets seem to embody that hope, rising in fire and thunder, as if tearing themselves free from gravity's grip. But confusing that symbol with reality means overlooking one of the defining challenges of our time. This misunderstanding becomes especially clear when we ask why returning to the moon proved far more difficult than it appeared. When Apollo astronauts first walked on the moon, it felt as though humanity had crossed a permanent boundary. Images of figures moving slowly across the pale surface, planting flags, gathering rocks, and gazing back at Earth suggested that the moon was merely the beginning. Broadcasts around the world implied that space travel had entered a new age, one in which journeys to the moon would become as routine as flights across the Atlantic. Watching a spacecraft leave Earth, travel 250,000 miles through space, land on another world, and return safely created the illusion of normality. Beneath that illusion, however, was an effort that was fragile, expensive, and astonishingly complex, stretching technology, finances, and human endurance to their absolute limits. The Apollo missions were remarkable achievements, but they were never sustainable in the way they seemed. One major reason for this gap between appearance and reality was cost. At its height, Apollo was among the most expensive projects ever undertaken by the United States. The program consumed billions of dollars during the 1,960 seconds, at a time when those sums were even more overwhelming than they sound today. Entire industries were mobilized to build the rockets, spacecraft, computers, and suits required to make the missions possible. Hundreds of thousands of people worked directly or indirectly on Apollo. The rockets themselves were immense, with the Saturn V remaining one of the most powerful machines ever constructed. Each launch was not only an engineering triumph, but also an economic one, demanding resources that were difficult to justify outside the political urgency of the Cold War. That urgency is another factor often forgotten when people wonder why humanity did not simply go back to the moon. The race to land there was driven not only by science or exploration, but by rivalry with the Soviet Union. The moon became a stage where two competing nations displayed power, technology, and ambition. Once the United States succeeded in landing astronauts and bringing them home safely, the symbolic objective was achieved. The world had witnessed American astronauts walking on another world, and for leaders at the time, that achievement was enough. Without the same political pressure, the enormous expense and danger of continuing regular missions lost their justification. Even during Apollo itself, risk was ever present. The missions were meticulously planned, yet they were also delicate. A spacecraft traveling to the moon and back was not robust in the way we often imagine. The lunar module that carried astronauts to the surface was thin, light, and fragile, built only to operate in the vacuum of space and the moon's weak gravity. Its walls were so thin that astronauts likened them to heavy-duty foil. If something had gone seriously wrong, there was no backup. Apollo 13 revealed just how close catastrophe could come. An explosion aboard the spacecraft forced the crew and mission control to improvise extraordinary solutions to bring the astronauts home alive. That mission ended without a landing, but it exposed how narrow the margin of safety truly was. The sheer complexity of these missions made repeating them even more difficult. Leaving Earth was only the beginning. The spacecraft had to separate, reconfigure, and ignite engines at precisely calculated moments to escape Earth orbit and set course for the Moon. Upon arrival, part of the spacecraft had to detach and descend, while another section remained circling above. After the surface mission, the two components had to meet again in lunar orbit, dock successfully, and then fire engines once more to head back toward Earth. In the end, only a small command module survived the plunge through the atmosphere, returning at tremendous speeds and protected solely by a heat shield. Every phase demanded perfect timing, exact calculations, and equipment that could not fail. Looking back today, landing on the Moon can seem almost straightforward. In reality, each mission was a long sequence of vulnerable steps where a single failure could have led to disaster. When Apollo came to an end, many expected humanity to press onward. Some imagined permanent bases on the Moon, while others envisioned journeys to Mars soon afterward. Instead, the opposite occurred. The Apollo program gradually wound down, and enthusiasm for spending at the same scale faded. The Vietnam War was draining national resources. Social programs and domestic priorities competed fiercely for funding. Political leaders saw little reason to continue investing billions in missions that no longer carried the same symbolic importance. By the middle of the 1970s, the Apollo era had closed, and there were no firm plans to return to the Moon. In the decades that followed, space exploration continued, but its focus shifted. The Space Shuttle was developed, offering reusable vehicles capable of carrying astronauts into low Earth orbit. In the 20th century, rockets carried humans beyond Earth for the very first time. We touched the Moon. We sent probes to every planet in the solar system. Suddenly, the idea of living on other worlds no longer seemed to belong only to our imagination. It felt like a future waiting to happen. But decades later, the dream has stalled. We have not returned to the Moon in half a century, and Mars remains as distant as ever. Every serious plan for a permanent human presence in space runs into problems that seem less like temporary setbacks and more like fundamental walls. What if humanity will never leave Earth for good? What if the idea of becoming a spacefaring species is not our destiny, but a fantasy? Why we mistake rocketry for simple freedom? When people think of rockets, the image that comes to mind is one of freedom. A sleek machine rising into the sky, flames pouring out beneath it, carrying humans away from the ground and into a new world. The countdown begins, the engines ignite, and suddenly the craft tears itself free from the planet. In just a few seconds, the ship seems to slip from Earth's grasp. For many, this image creates the belief that rockets are simple tools for liberation, a fast ticket to anywhere beyond the sky. Yet the truth is far from simple. Rockets are not symbols of casual escape. They are machines that fight against the strongest force we know in our daily lives, Earth's gravity. And they do so at a cost that people rarely acknowledge. From early science fiction novels to modern blockbusters, rockets have been painted as near magical vehicles. A hero needs to leave Earth. The ship is waiting on the launch pad, and within a few minutes, it breaks into orbit. These portrayals compress months or even years of planning into a single moment of dramatic ascent. The engines roar, the camera shakes, and before long the characters are weightless. There is rarely mention of the staggering quantities of fuel required, the detailed calculations of trajectory, or the hair, thin margin of error between success and catastrophe. Movies and shows smooth away the difficulties, leaving the impression that flight beyond Earth is no more complex than catching a long-distance train. Human beings are used to planes. We board them, sit in a chair, and within hours find ourselves on the other side of the planet. The leap from plane to rocket feels, in cultural imagination, like an extension of the same idea. If a plane can cross oceans, surely a rocket can cross space. But the two are not the same. A plane moves through air, lifted by wings and powered by engines that sip oxygen directly from the atmosphere. A rocket must carry all of its own oxygen and fuel, burning it at an incredible rate just to rise above the pull of the planet. To reach orbit, a spacecraft must travel at more than 28 kilometers per hour. This speed is not a luxury but a requirement. Anything slower and the craft will fall back, crashing to the Earth it tried to leave. The cost of achieving this speed is almost unimaginable. A modern rocket, like those used to send satellites or astronauts into space, carries hundreds of tons of propellant. Most of the structure we see on the launch pad is not the spacecraft at all, but the fuel needed to push it upward. The actual capsule or satellite, the thing that survives the journey and continues into orbit, makes up only a tiny fraction of the total mass. In fact, around 90% or more of a rocket's weight at launch is fuel. The vehicle sacrifices itself in stages, dropping empty tanks to shed weight, just so that a small piece of it can continue the journey. What looks like freedom is actually an enormous, carefully timed act of destruction, where much of the rocket is left behind in the attempt to escape gravity's hold. During the space race of the 1,960 seconds, rockets became icons of possibility. They represented progress, power, and even hope. Images of Apollo launches made their way into homes around the world, showing flames, thunder, and triumph. What was rarely shown was the years of failure that came before. The destroyed prototypes, the astronauts lost in training accidents, and the countless calculations that had to be done before a single launch was even attempted. The public was fed the highlights, the heroic successes, which cemented the idea that rockets were clean paths to the stars. The messy reality, full of trial and error, remained in the background. The simplification continues in modern times. Private companies broadcast their launches with sleek visuals and celebratory language. They promise futures where rockets may one day carry people between cities or even to Mars, as though it is only a matter of waiting for the tickets to go on sale. The true challenges, engineering reliability, human safety, resource costs, are often left in the fine print. This is not deception so much as it is marketing. Spectacle sells, and nothing captures attention like the sight of a rocket cutting upward against the sky. The danger is that this repetition of simplified images builds a cultural memory where rockets equal easy departure, where leaving Earth is no more complicated than leaving a driveway. But to leave Earth is to push against one of the most stubborn barriers in nature, gravity by itself, to the planet. It holds oceans in place, keeps the air around us, and shapes the very path of the moon. To escape its pull requires not just power, but precision. A rocket cannot simply go straight up and keep climbing. If it did, it would eventually run out of fuel and fall back down. Instead, it must arc sideways, gradually building up speed until it is moving so fast that Earth's curve drops away beneath it. This motion is more like falling around the planet than leaving it. ChatGPT Danoi. In the 20th century, rockets carried human beings beyond Earth for the first time. We stood on the surface of the moon. We sent robotic explorers to every planet in the solar system. In that moment, the idea of living on other worlds no longer belonged solely to imagination. It felt tangible, like a future already opening its door. And yet, decades later, that momentum has slowed. We have not returned to the moon for half a century, and Mars remains stubbornly remote. Every serious attempt to establish a permanent human presence beyond Earth collides with obstacles that feel less like temporary delays and more like hard limits. It raises an unsettling question. What if humanity never truly leaves Earth behind? What if becoming a spacefaring species is not an inevitable destiny, but a beautiful illusion? And why do we so often confuse rocketry with freedom? When people picture rockets, they imagine freedom itself, a slender machine rising skyward, fire pouring from beneath, lifting human lives away from the ground toward a new world. The countdown reaches 0, engines ignite, and the vehicle appears to tear itself loose from the planet. In a matter of seconds, it seems to slip from Earth's grasp. This image convinces many that rockets are simple instruments of escape, swift tickets to anywhere beyond the sky. But the reality is far more complex. Rockets are not symbols of effortless departure. They are machines built to fight the most powerful force we experience in everyday life, Earth's gravity. And they do so at an extraordinary cost, one that is rarely acknowledged. From early science fiction to modern cinema, rockets are often portrayed as almost magical. A hero needs to leave Earth, the ship waits on the launch pad, and within minutes it reaches orbit. Entire months, sometimes years, of preparation are compressed into a single dramatic ascent. The engines thunder, the camera trembles, and soon the characters float weightless. Missing from these stories are the immense volumes of fuel required, the meticulous calculations of trajectory, and the impossibly narrow margin between success and disaster. Film and television polish away the difficulties, leaving the impression that leaving Earth is no more complicated than boarding a long journey train. We are familiar with airplanes. We step aboard, sit comfortably, and hours later arrive on the other side of the planet. In our collective imagination, the jump from airplane to rocket feels like a natural extension of the same idea. If an aircraft can cross oceans, then surely a rocket can cross space. But the two could not be more different. An airplane moves through air, supported by wings and powered by engines that draw oxygen directly from the atmosphere. A rocket must carry every molecule of oxygen it needs, along with its fuel, and burn both at a ferocious rate simply to rise against the planet's pull. To remain in orbit, a spacecraft must reach a speed greater than 28,000 kilometers per hour. This speed is not optional. Anything less, and the vehicle will fall back, returning violently to the Earth it tried to escape. The price of reaching that velocity is staggering. Modern rockets, whether launching satellites or astronauts, carry hundreds of tons of propellant. What we see standing on the launch pad is mostly fuel. The spacecraft itself, the part that survives and continues into orbit, is only a small fraction of the total mass. Around 90% or more of a rocket's launch weight is fuel. As it climbs, the rocket sheds itself in stages, discarding empty tanks to reduce weight, all so that a small remnant can continue onward. What appears to be freedom is, in truth, a vast and precisely timed act of sacrifice, where most of the vehicle is abandoned in the struggle to escape gravity's grip. During the space race of the 1,960 seconds, rockets became powerful symbols of possibility. They stood for progress, strength, and hope. Images of Apollo launches filled living rooms across the world, full of flame, thunder, and triumph. Rarely seen were the years of failure that preceded them, the shattered prototypes, the lives lost in training, and the endless calculations completed before a single launch was attempted. The public saw the victories, and those victories shaped the belief that rockets offered clean and direct paths to the stars. The untidy reality remained hidden. That simplification continues today. Private companies stream launches with elegant visuals and celebratory language. They speak of futures where rockets carry people between cities or onward to Mars, as though it is merely a question of patience before tickets appear. The deeper challenges, engineering reliability, human safety, and immense resource demands, are often confined to the margins. This is not deception so much as marketing. Spectacle sells, and few sights are as arresting as a rocket climbing into the sky. The danger lies in repetition. Over time, these simplified images build a shared memory in which rockets mean easy departure, where leaving Earth seems no more complicated than reversing out of a driveway. But to leave Earth is to confront one of nature's most unyielding barriers, gravity itself. Gravity anchors the oceans, holds the atmosphere in place, and governs the motion of the moon. Escaping it demands not only raw power, but exquisite precision. A rocket cannot simply rise straight upward forever. If it did, fuel would run out and it would fall back. Instead, it must curve sideways, steadily accelerating until it moves so fast that the curvature of Earth drops away beneath it. In this sense, orbit is not an escape at all, but a continuous fall around the planet. To maintain orbit, the rocket must reach the perfect balance of height and speed. Every launch is the product of thousands of people, years of effort, and billions of dollars. What looks like liberation from Earth is, in fact, the most constrained and difficult kind of travel we have ever attempted. Popular culture erases this struggle because stories are easier to tell when the machines simply work, when the heroes reach space without confronting the full weight of what it takes to get there. Yet behind every smooth image of ascent is a hidden mountain of effort. We want to believe that the sky is open, that we are only a few steps away from leaving behind all the problems of Earth. Rockets embody that dream in shape and motion, rising on fire and thunder as if tearing the chains of gravity apart. But to mistake that symbol for reality is to overlook the challenge that still defines our age. Why? Returning to the moon was harder than it looked. When the Apollo astronauts first set foot on the moon, it seemed as though humanity had crossed a permanent threshold. Images of astronauts moving slowly across the grey surface, planting flags, collecting rocks, and looking back toward Earth gave the impression that the moon was only the beginning. The way it was broadcast around the world suggested that space travel had entered a new era, one where visits to the moon would become as regular as flights across the Atlantic. The sight of a spacecraft leaving Earth, traveling 250,000 miles through space, landing on another world and returning safely, created the illusion of routine. Yet beneath that illusion was a fragile, costly, and deeply complex effort that pushed technology, money, and human endurance to their limits. The Apollo missions were extraordinary achievements, but they were never sustainable in the way they appeared. One reason for this gap between appearance and reality was cost. Apollo was, at its peak, one of the most expensive projects ever undertaken by the United States. The program consumed billions of dollars in the 1,960 seconds. At a time when those amounts were even more staggering than they sound today, entire industries were mobilized to build the rockets, spacecraft, computers, and suits that would make the missions possible. Hundreds of thousands of people worked directly or indirectly on Apollo. The rockets themselves were enormous, with the Saturn V still standing as one of the most powerful machines ever built. Each launch was not just an engineering feat, but an economic one, demanding resources that could not be easily justified outside of the political urgency of the Cold War. That urgency was another factor often overlooked when people wonder why humanity did not simply return to the moon. The race to land there was not driven only by science or exploration. It was fueled by competition with the Soviet Union. The moon became a stage on which two rival nations demonstrated power, technology, and ambition. Once the United States succeeded in landing astronauts and returning them home safely, the symbolic goal was achieved. The world had seen American astronauts walking on another world, and in the eyes of leaders at the time, that victory was enough. Without the same level of political pressure, the enormous costs and risks of continuing regular missions lost their justification. Even during the Apollo program itself, the risks were constant. The missions were carefully planned and executed, but they were also fragile. A spacecraft traveling to the moon and back was not robust in the way we often imagine. The lunar module that carried astronauts down to the surface was thin, lightweight, and delicate. It was designed only to work in the vacuum of space and under the low gravity of the moon. Its walls were so thin that astronauts compared them to heavy-duty foil. If anything had gone seriously wrong, there was no backup. Apollo 13 famously showed just how close disaster could come. An explosion in the spacecraft forced the crew and mission control to improvise solutions to bring the astronauts home alive. That mission ended without a landing, but it revealed how narrow the margin of safety truly was. The complexity of these missions added to the difficulty of repeating them. Launching from Earth was only the first step. The spacecraft had to separate, reconfigure, and fire engines at precise moments to escape Earth orbit and aim for the moon. Once there, part of the spacecraft had to break away and descend, while another part remained in orbit. After the surface mission, The two had to reunite in lunar orbit, dock together, and then fire engines again to return to Earth. Finally, only a small command module survived re-entry through the atmosphere, plunging back at tremendous speeds and surviving by means of a heat shield. Every stage involved delicate timing, exact calculations, and equipment that could not fail. When people today look back, it can seem as though landing on the moon was straightforward. But in truth, each mission was a long chain of fragile steps, each of which could end in disaster if anything went wrong. After Apollo ended, the expectation among many was that humanity would keep going. Some thought that permanent lunar bases would be built, while others dreamed of Mars missions following soon after. Instead, the opposite happened. The Apollo program wound down, and there was little appetite to spend at the same level again. The Vietnam War was draining American resources. Social programs and other domestic priorities competed for funding. Politicians saw little reason to continue pouring billions into missions that no longer carried the same symbolic weight. By the mid-1970 seconds, the Apollo era was over, and there were no concrete plans to return to the moon. In the decades that followed, space exploration did not end, but its focus shifted. The space shuttle was developed, offering reusable vehicles that could carry astronauts into low Earth orbit. To remain in orbit, a rocket must achieve an exact balance between altitude and velocity. Every launch represents the combined work of thousands of people, years of dedication, and billions of dollars. What appears to be freedom from Earth is, in reality, the most restrictive and demanding form of travel humanity has ever attempted. Popular culture smooths away this struggle because stories are simpler when machines function perfectly, when heroes reach space without confronting the true weight of what it takes to get there. Yet behind every graceful image of ascent lies an unseen mountain of effort. We want to believe the sky is open, that we are only a few steps away from escaping the troubles of Earth. Rockets seem to embody that hope, rising in fire and thunder, as if tearing themselves free from gravity's grip. But confusing that symbol with reality means overlooking one of the defining challenges of our time. This misunderstanding becomes especially clear when we ask why returning to the moon proved far more difficult than it appeared. When Apollo astronauts first walked on the moon, it felt as though humanity had crossed a permanent boundary. Images of figures moving slowly across the pale surface, planting flags, gathering rocks, and gazing back at Earth suggested that the moon was merely the beginning. Broadcasts around the world implied that space travel had entered a new age, one in which journeys to the moon would become as routine as flights across the Atlantic. Watching a spacecraft leave Earth, travel 250,000 miles through space, land on another world, and return safely created the illusion of normality. Beneath that illusion, however, was an effort that was fragile, expensive, and astonishingly complex, stretching technology, finances, and human endurance to their absolute limits. The Apollo missions were remarkable achievements, but they were never sustainable in the way they seemed. One major reason for this gap between appearance and reality was cost. At its height, Apollo was among the most expensive projects ever undertaken by the United States. The program consumed billions of dollars during the 1,960 seconds, at a time when those sums were even more overwhelming than they sound today. Entire industries were mobilized to build the rockets, spacecraft, computers, and suits required to make the missions possible. Hundreds of thousands of people worked directly or indirectly on Apollo. The rockets themselves were immense, with the Saturn V remaining one of the most powerful machines ever constructed. Each launch was not only an engineering triumph, but also an economic one, demanding resources that were difficult to justify outside the political urgency of the Cold War. That urgency is another factor often forgotten when people wonder why humanity did not simply go back to the moon. The race to land there was driven not only by science or exploration, but by rivalry with the Soviet Union. The moon became a stage where two competing nations displayed power, technology, and ambition. Once the United States succeeded in landing astronauts and bringing them home safely, the symbolic objective was achieved. The world had witnessed American astronauts walking on another world, and for leaders at the time, That achievement was enough. Without the same political pressure, the enormous expense and danger of continuing regular missions lost their justification. Even during Apollo itself, risk was ever present. The missions were meticulously planned, yet they were also delicate. A spacecraft traveling to the moon and back was not robust in the way we often imagine. The lunar module that carried astronauts to the surface was thin, light, and fragile, built only to operate in the vacuum of space and the moon's weak gravity. Its walls were so thin that astronauts likened them to heavy-duty foil. If something had gone seriously wrong, there was no backup. Apollo 13 revealed just how close catastrophe could come. An explosion aboard the spacecraft forced the crew and mission control to improvise extraordinary solutions to bring the astronauts home alive. That mission ended without a landing, but it exposed how narrow the margin of safety truly was. The sheer complexity of these missions made repeating them even more difficult. Leaving Earth was only the beginning. The spacecraft had to separate, reconfigure, and ignite engines at precisely calculated moments to escape Earth orbit and set course for the moon. Upon arrival, part of the spacecraft had to detach and descend, while another section remained circling above. After the surface mission, the two components had to meet again in lunar orbit, dock successfully, and then fire engines once more to head back toward Earth. In the end, only a small command module survived the plunge through the atmosphere, returning at tremendous speeds and protected solely by a heat shield. Every phase demanded perfect timing, exact calculations, and equipment that could not fail. Looking back today, landing on the moon can seem almost straightforward. In reality, each mission was a long sequence of vulnerable steps where a single failure could have led to disaster. When Apollo came to an end, many expected humanity to press onward. Some imagined permanent bases on the moon, while others envisioned journeys to Mars soon afterward. Instead, the opposite occurred. The Apollo program gradually wound down, and enthusiasm for spending at the same scale faded. The Vietnam War was draining national resources. Social programs and domestic priorities competed fiercely for funding. Political leaders saw little reason to continue investing billions in missions that no longer carried the same symbolic importance. By the middle of the 1970 seconds, the Apollo era had closed, and there were no firm plans to return to the moon. In the decades that followed, space exploration continued, but its focus shifted. The space shuttle was developed, offering reusable vehicles capable of carrying astronauts into low Earth orbit. Instead of traveling outward, missions focused on building infrastructure closer to home. Satellites, space stations, and telescopes became the main tools of exploration. While these projects advanced science in many ways, they reinforced the idea that venturing back to the moon was not a priority. The shuttle program itself, though ambitious, consumed large amounts of funding and required constant maintenance. The International Space Station absorbed even more resources. With so much invested in near-Earth operations, there was little room left for lunar expeditions. Technological challenges also made a return harder than it seemed. Although Apollo had succeeded, it did not leave behind a robust, ready-to-use system for future missions. The Saturn V rockets were retired, and the production lines that built them were dismantled. The specialized skills and knowledge faded as workers moved on and the years passed. Rebuilding that capability from scratch would require a massive investment of money and time. The idea that humanity could simply dust off the plans and return to the moon ignored how quickly aerospace technology changes and how difficult it is to recreate the infrastructure of the 1960 seconds and 70 seconds decades later. Another factor was the human perception of danger. Apollo astronauts were willing to face enormous risks. The missions were dangerous, and those involved knew it. But as time passed, public tolerance for risk in spaceflight decreased. Each tragedy, such as the Challenger and Columbia shuttle disasters, reminded the world of the human cost when things went wrong. These events made governments and agencies more cautious. The moon, with its distance and difficulty, seemed too dangerous for missions that did not have a clear purpose beyond prestige. Exploration gave way to caution, and caution slowed progress. The question of why we have not simply gone back often assumes that technology naturally advances in a straight line. In many fields, progress is steady and builds upon itself. But space exploration does not work in the same way. It depends heavily on funding, politics, and priorities. The Apollo missions were not the start of an inevitable march outward. They were a peak made possible by unique circumstances, a mix of competition, ambition, and national pride. Once those circumstances faded, the peak was followed by a decline. Returning to the moon required more than just desire. It required rebuilding the massive framework that Apollo had relied upon, and without strong reasons to do so. That framework never materialized again. In recent years, talk of returning has resurfaced, fueled by new technology and new players. Private companies promise lower costs and innovative designs, while nations see the moon once again as a strategic and symbolic goal. Yet the long gap since Apollo shows just how hard it truly was. The dream of a simple return was always an illusion, built on memories of televised triumphs rather than the reality of fragile machines and extraordinary costs. The moon has always been within sight, but reaching it is a reminder that what looks routine in history books or documentaries was, in fact, one of the hardest things humanity has ever done. The rocket equation's paywall. The rocket equation was worked out in the early 20th century by Konstantin Tsiolkovsky, one of the pioneers of spaceflight theory. At its heart, the equation simply describes how the velocity of a rocket depends on how fast its exhaust gases are pushed out, and on how much of the rocket's starting mass is fuel. On paper, it looks like a clean formula. In practice, it dictates everything about what rockets can and cannot do. It reveals that rockets can only reach higher speeds by throwing away a huge percentage of their own starting mass. The more speed you need, the larger that sacrificed fraction becomes. For missions that require escaping Earth's gravity, that percentage becomes enormous. This is why rockets look the way they do. The consequences of this equation are punishing. Suppose you want to send a heavier object into space, like a larger satellite, or even a spacecraft capable of carrying supplies for long journeys. The instinct might be to simply build a bigger rocket, but the rocket equation resists this idea. As the payload gets heavier, the rocket must carry more fuel to push it. That added fuel itself adds weight, which demands still more fuel. This loop quickly spirals out of control. A rocket large enough to send truly heavy loads into deep space would need to carry so much fuel that it becomes almost absurdly big. Even if you could build it, the cost and engineering challenges would be staggering. This is why most of the rockets we see launched today look similar in scale, despite advances in technology. They are all fighting the same mathematical barrier. To push against Earth's gravity well, they must devote nearly all of their structure to fuel. The payload remains tiny compared to the whole. In some cases, only a few % of the launch mass makes it into orbit. The rest is fuel burned away, or discarded tanks falling back into the ocean. This imbalance is baked into the physics of how rockets work. One way engineers have tried to deal with this problem is through staging. A single rocket carrying all of its fuel in one piece would be so heavy that it could never escape the cycle of adding more and more propellant. By splitting the rocket into stages, engineers can drop empty fuel tanks and engines as they are used up. This reduces weight step by step, making it possible for the remaining stages to accelerate further. Staging does not break the rocket equation, but it works with it, allowing us to squeeze more performance out of the same math. Without staging, the moon landings would never have been possible. The Saturn V rocket, for all its power, could not have carried its payload to the moon in one piece. It succeeded only because it shed parts of itself along the way, like a tree shedding branches, to let the core climb higher. Yet even staging has limits. If you want to send something much farther than the moon, say, a crewed mission to Mars, you face the same wall. The spacecraft will need not just enough fuel to leave Earth, but also fuel to slow down when it arrives, and then more fuel to leave Mars and come back. Every drop of that fuel has to be carried from the start, stacked on top of itself, magnifying the weight and feeding the cycle once more. In theory, you could keep adding stages, but in practice, this becomes unwieldy. A rocket tall enough to hold all that propellant would be too large to build or launch. The costs would skyrocket long before the rocket itself did. This is where the dream of building ever bigger rockets runs into reality. People often imagine a future where we simply build machines large enough to carry whole colonies of people and supplies across the solar system. Science fiction fills our imagination with vast ships lifting effortlessly from the ground, as if progress was simply a matter of building larger factories. But the rocket equation explains why this vision does not translate easily into reality. Growth is not linear, it is exponential. Each step forward demands far more than the one before it. The leap from launching a small satellite to sending a heavily loaded spacecraft is enormous within the limits of current rocketry. Some have tried to bypass this barrier by proposing alternative forms of propulsion. Nuclear thermal rockets, for instance, would use reactors to heat propellant instead of burning chemical fuel, producing higher exhaust speeds and improved performance under the rocket equation. Other concepts, such as ion engines, solar sails, or fusion propulsion, aim to push against these limits by offering far greater efficiency. Yet for now, these ideas remain experimental or theoretical. Today's launches still depend on chemical propellants, and chemical rockets remain bound to the severe trade-offs dictated by Tsiolkovsky's mathematics. Satellites, space stations, and telescopes in orbit are achievable with existing rockets, though they require meticulous planning and enormous investment. Missions that venture farther, such as probes sent to Mars or beyond, are far less common because each one strains the limits of how much mass can be delivered. When humans replace machines, the difficulty increases dramatically. Life support systems, radiation shielding, food supplies, and the capacity to return all add mass. Every added kilogram demands more fuel, and the cycle begins again. This reality has shaped not only rocket technology, but the rhythm of exploration itself. It explains why, so many decades after the moon landings, humans have not traveled farther. The obstacle is not merely money or politics, though both matter greatly. The deeper problem is that rockets are constrained by a law that makes scaling up brutally expensive. It is not a lack of imagination. It is that imagination collides with physics, and the rocket equation always prevails. To those who dream, the equation feels like a chain, setting hard limits on what can be attempted with present tools. For rocket designers, it is a constant challenge that forces every decision to be guided by efficiency. Fuel tanks, engines, and systems are all shaped by the unforgiving balance between mass and speed. This is why a rocket on the launch pad appears impossibly large, yet carries only a small capsule at its tip. Almost everything visible is fuel, and almost nothing that truly matters survives to orbit. The rocket equation does not forbid leaving Earth, but it demands such a high price that only the most carefully designed missions can afford it. Every ambition to go farther, to Mars, to asteroids, or to distant stars, encounters this barrier until new propulsion methods or entirely new concepts of travel are found. Rockets therefore remain machines that offer only limited freedom. Chemical rockets and their limits reveal this clearly. Chemical propulsion is an unlikely foundation for something as bold as space exploration. Its principle is simple. Fuel and oxidizer are combined and ignited, releasing energy violently. Exhaust gases are expelled at high speed through a nozzle, pushing the rocket in the opposite direction. It is a direct expression of Newton's third law, that every action has an equal and opposite reaction. For centuries, this idea existed mainly in fireworks and early experiments, never intended to carry people to other worlds. Yet even today, after decades of technological progress, we still rely on it. Chemical propulsion has carried every astronaut into space, every satellite into orbit, and every probe on its initial journey away from Earth. At the same time, it has confined us to a narrow range of possibilities. It is powerful, but only just sufficient. It works, but at extraordinary cost. It is both the foundation of spaceflight and its greatest limitation. The engines of launch vehicles such as the Saturn V or the SpaceX Falcon 9 generate millions of pounds of thrust. This immense force is required to lift a spacecraft out of Earth's gravity well, one of the most demanding challenges in spaceflight. No other propulsion system available today can deliver such immediate power. Nuclear engines, ion drives, or solar sails may promise higher efficiency, but they cannot yet produce the raw force needed for the first step, leaving the ground. For this reason, chemical rockets remain essential, the only tools capable of bridging the gap between Earth's surface and orbit. Once that gap is crossed, their limitations become obvious. Chemical rockets consume fuel at astonishing rates. During launch, thousands of liters of propellant can be burned every second. This fuel does not scale well. As mission mass increases, the rocket equation ensures fuel demands expand beyond practical limits. Efficiency is brutally low. The trade-off grows harsher for missions beyond Earth orbit. Every additional maneuver requires more fuel. When humans are involved, the problem intensifies. Machines can be stripped down to essentials, but humans need food, water, air, shielding, and space to live. Each requirement adds mass, which demands more fuel, which adds still more mass. Chemical rockets must also carry everything they need from the start. Fuel and oxidizer are loaded before launch, with no possibility of refueling once the engines fire. When the tanks are empty, the rocket's role is finished. This restricts both range and flexibility. A chemical rocket can perform only the mission it was designed for. If conditions change or greater distances are required, there is little margin. Propellant is a fixed budget, and once it is spent, the mission ends. These limits explain why the most distant spacecraft ever built are small robotic probes. Voyagers 1 and 2, launched in the 1,970 seconds, are now the farthest human-made objects in space. They did not reach those distances by carrying fuel for billions of kilometers. Instead, they used carefully planned paths, gaining energy from planetary flybys. Without these gravity assists, chemical propulsion alone would not have been enough. Even then, the probes are tiny compared to crewed spacecraft, and their journeys relied heavily on external help. This sharp boundary defines what chemical rockets can do. They can deliver small, precisely engineered machines across vast distances, but not heavy cargo or large crews. Despite these limitations, we continue to depend on chemical rockets because no alternative has yet matched their reliability. Ion engines can operate for years with remarkable efficiency, but their thrust is far too gentle to lift a vehicle from Earth. Nuclear propulsion promises higher performance, but carries serious safety and political challenges. Solar sails require enormous, fragile structures deployed in space. Until such technologies mature, chemical rockets remain the only practical way to reach orbit and beyond. Trying to carry enough supplies for a Mars colony, along with equipment for survival and return journeys, quickly becomes impossible using chemical fuel. Even attempting such a mission would require an extraordinary number of launches to assemble the necessary mass in orbit. Each launch would cost hundreds of millions of dollars and depend on precise timing and success. The vision collapses under the weight of fuel limits. The challenge grows even greater for journeys beyond Mars. Reaching Jupiter, Saturn, or more distant destinations demands travel times of years or decades. Carrying sufficient chemical fuel for such voyages is not feasible. Probes can succeed because they are small, require minimal power, and exploit carefully chosen trajectories. For missions that carry human beings, with all their immense demands, chemical propulsion simply cannot deliver enough capability. It is remarkable, then, that our entire era of spaceflight has been built on this single approach. From the first launches of the 20th century to the most advanced rockets flying today, the core principle has remained unchanged. Engines have grown more reliable, fuels slightly more efficient, and designs far more refined, yet the basic method is the same one used in the earliest experimental rockets. In many other fields, technology advances at a rapid pace. Computers shrink while growing more powerful. Energy systems diversify and evolve. Rocketry, by contrast, has remained anchored to chemical propulsion for decades. That fact reveals both how far this method has taken us and how stark the limits become when one tool is pushed beyond what physics comfortably allows. Behind every launch lies a hidden mass of support: launch pads, fuels, supply chains. An invisible network of infrastructure supports every rocket, remaining on Earth, yet proving just as essential as the engines themselves. Without this ground-bound foundation, no spacecraft would ever rise beyond the atmosphere. The rocket is only the visible performer. The stage on which it stands is vast, heavy, and extraordinarily expensive. Consider the launch pad. From afar, it appears to be little more than a slab of concrete with a tower nearby. In reality, it is an immense feat of engineering. A launch pad must not only hold a rocket upright, but survive the extreme violence of ignition. Exhaust from chemical rockets reaches thousands of degrees, and the resulting pressure waves can destroy concrete if not carefully managed. This is why flame trenches, water deluge systems, and sound suppression structures are integral to modern pads. During a launch, billions of liters of water may be released in seconds to absorb heat and dampen sound waves that could otherwise rebound and damage the vehicle. None of this can be reused. After each launch, pipes must be replaced, valves serviced, and concrete repaired. Every flight scars the infrastructure, demanding large crews and continuous investment simply to restore the site. Beyond the pad itself rise the towers. These are not simple scaffolds, but complex service structures packed with access arms, fueling lines, and safety systems. They allow technicians to reach payload bays, load cryogenic propellants, and stabilize the rocket against wind. Constructing such a tower can cost hundreds of millions, and once built, it cannot be easily moved. Each launch pad becomes a permanent monument, bound to its location, climate, and political setting. When nations discuss new launch sites, they are not talking about weeks or months of work, but years of construction and billions of dollars devoted to infrastructure that may support only a few launches each year. Fuel represents another hidden weight. Chemical rockets depend on cryogenic propellants such as liquid hydrogen and liquid oxygen, which must be manufactured, transported, and stored under extreme conditions. Liquid hydrogen boils away just a few degrees above absolute zero, requiring tanks lined with sophisticated insulation. Even then, losses are unavoidable. Simply keeping the fuel from evaporating is a continuous struggle against physics. Producing these propellants consumes enormous amounts of energy. Large industrial facilities operate constantly to meet launch schedules. Every tank of fuel carries not only chemical energy, but the vast energy cost of making it usable. Transporting that fuel from plant to launch site adds another layer of complexity. Specialized vehicles, pipelines, and storage tanks are required, each governed by strict safety rules. A single mishap anywhere along this chain can delay launches for weeks or months, because rocket fuels are so volatile that contamination or mishandling is disastrous. At the launch site, fueling can take hours. Teams of highly trained technicians in protective gear monitor every step, watching for leaks. A small hydrogen leak, invisible and nearly impossible to detect without sensors, can trigger an explosion powerful enough to destroy the rocket and the entire facility. Fueling is therefore not just an engineering task, but a precise and costly choreography of safety and control. Yet pads and propellants are only the surface. Beyond them stretches a global supply chain. A single rocket may include millions of components sourced from dozens of countries. Metals are mined, refined, and machined into exact shapes. Electronics are produced in clean rooms that themselves cost hundreds of millions to operate. Every bolt, wire, and circuit is tracked, tested, and certified. Building a rocket is not a simple construction project. It is the orchestration of industries across national and international boundaries. Just as an aircraft relies on airports, control towers, and maintenance crews, a rocket depends on an entire world of infrastructure, but on a far larger scale, because tolerances are unforgiving. Thousands of people work not only at launch sites, but in factories, laboratories, and transport networks that support spaceflight. Their efforts remain mostly unseen. Engineers ensure cryogenic lines hold. Welders assemble tanks designed to withstand immense pressures. Logistics teams schedule deliveries down to the hour. Many of these people will never witness the rocket they helped create, yet without them it would never exist. This invisible burden is one reason launches remain rare, even in the 21st century. Unlike airplanes, which operate from thousands of airports worldwide, rockets are bound to a handful of specialized pads. Each launch demands months of preparation and the coordination of massive supply systems. When a rocket fails, the loss extends beyond hardware. Entire industrial schedules are disrupted, recovery takes time, and time costs money. This is why nations guard their launch sites so carefully, and why private companies, despite advances in reusability, still operate from only a few locations worldwide. Even after a successful launch, the infrastructure remains grounded. Pads are inspected, flame trenches repaired, tanks refilled, trucks arrive with replacement parts. Technicians swap out worn components. New shipments of fuel arrive by rail or ship. The cycle continues, long after the rocket has disappeared into the sky. Maintaining this cycle demands budgets measured in billions, ensuring that spaceflight remains among the most expensive pursuits humanity has ever attempted. A launch site is a strategic asset. Its location affects efficiency, its capacity influences national standing, and its vulnerabilities raise security concerns. Building and maintaining such a site binds a nation's economy and politics to the infrastructure itself. Decisions about launches are never purely scientific. They involve supply chains, budgets, and commitments that stretch across decades. An airplane needs fuel, a runway, and a crew, all readily available around the world. A rocket requires a cathedral of steel and concrete, filled with machinery built for a single purpose. Every launch consumes part of its stage, demanding continual rebuilding. Until propulsion changes at a fundamental level, this tether to Earth will remain. Rockets may rise into the sky, but their paths are carved deep into the ground, anchored by infrastructure far too massive to follow them into space. This is why reuse alone does not solve the problem. In recent years, the return of rocket boosters has been celebrated as a revolution. Watching a towering stage descend and land upright on a drone ship seems almost unreal. The economic appeal is obvious. Instead of discarding a booster after one flight, it can be used again. Airplanes are not scrapped after a single journey, so why should rockets be? Companies such as SpaceX have shown that booster reuse can significantly reduce costs compared to earlier approaches. Yet even this advance is an extension, not a cure. Reusability does not eliminate the fuel problem. A reusable booster still needs immense tanks of propellant to rise from the ground. Each flight demands the same vast quantities of liquid oxygen and kerosene or methane to be produced, stored, and transported. Fuel costs are lower than the cost of the booster itself, but they are far from trivial, especially when launches become frequent. The rocket equation remains unchanged. No matter how many times a booster is reused, it still confronts the same harsh trade-off between fuel mass and payload mass. Reuse lowers the cost per launch, but it does not allow rockets to carry dramatically more into space. Another constraint lies in maintenance. A booster is not comparable to a commercial aircraft designed for tens of thousands of flights between major overhauls. Each landing subjects the structure to extreme stress. Engines endure intense heat, pressure, and vibration. Even with flawless landings, wear accumulates. After every mission, teams of engineers must inspect, repair, and often replace components before the rocket can fly again. This refurbishment is slow and expensive. Reusability is not a simple cycle of launch, landing, and refueling. It more closely resembles rebuilding a race car after each competition. The booster survives only through sustained effort and cost. Upper stages present an even greater challenge. While lower stages can be recovered because they never reach orbital speed, upper stages usually burn up in the atmosphere or remain in orbit as debris. Recovering and reusing them is far more difficult because they travel much faster and are harder to slow down. Without reusable upper stages, efficiency continues to be eroded by the rocket equation. Even if the lower half of a rocket returns, the upper half is still lost, along with its engines, tanks, and avionics. The vision of a fully reusable two-stage rocket remains largely unproven. And even if it becomes reality, the laws of physics will not suddenly allow rockets to transport vast populations into orbit cheaply. Staging and reuse also fail to solve the problem of scale. Launching small payloads, satellites, scientific instruments, or even limited crews is possible with current rockets. Colonization implies something entirely different. It implies millions of tons of cargo, habitats, food, water, and people moving through space. The numbers involved are overwhelming. Even the most optimistic reusable rocket concepts fall far short of moving material on this scale. If constructing a modest space station requires dozens of launches and years of assembly, imagine the demands of building cities on the Moon or Mars. Every kilogram must be justified, and every launch still consumes fuel on an industrial scale. The infrastructure supporting reusable rockets is no less massive than that required for expendable ones. Landing pads, drone ships, tracking networks, and refurbishment facilities all add layers of complexity and expense. While rockets return, the support systems on Earth remain just as heavy. Each booster needs a dedicated team, hangar space, and a continuous supply of replacement parts. This dependence on ground infrastructure limits flight frequency. Rockets cannot yet operate with anything like the regularity and simplicity of airplanes, regardless of how often they are reused. The core issue remains that chemical rockets are operating at the edge of what their fuel can provide. The energy density of chemical reactions is simply too low to overcome the rocket equation in a transformative way. Staging removes dead weight, and reuse reduces waste, but neither changes the fact that most of a rocket is still fuel. These innovations are clever, but they are incremental responses to a problem that demands a fundamentally different solution. Think of a ladder leaning against a cliff. Staging and reuse add a few extra rungs, or reuse the same materials. They help us climb a little higher, but the cliff still towers above. To reach the top, we would need not a better ladder, but an entirely new way of climbing. This is why such innovations, important as they are, cannot on their own enable mass colonization. They expand the margins, but they do not break through the limits imposed by physics. Even with perfect reuse, the cost of transporting large masses remains immense. Every colony ship would require dozens, or perhaps hundreds of launches to assemble and fuel. Each launch would demand its own infrastructure, its own vast quantities of fuel, and its own workforce. Colonization is not about cutting costs in half. It is about differences measured in orders of magnitude. And the rocket equation does not yield by orders of magnitude. The logistical reality, the unglamorous need for constant supply, is often overlooked. Images of settlements on the Moon or Mars are typically polished and serene. Transparent domes shine under alien skies. Machines hum softly. Settlers move confidently in advanced suits, as if survival is assured. Popular imagination fixates on arrival, the first step, the first flag, the symbolic beginning. But a colony cannot live on symbolism. It survives on supplies. Tools fail, food is consumed, air filters clog. Every breakdown requires replacements delivered from Earth. The true challenge of long-term survival in space is not arrival, but endurance. History on Earth offers clear parallels. When humans crossed oceans to establish new settlements, they depended on constant resupply. Food, clothing, tools, timber, and medicine arrived in regular shipments. When those supply lines failed, colonies collapsed. The Jamestown settlement, for example, nearly starved when resupply ships were delayed. The difference between Earth and space is scale. Ships crossing oceans carried tons of cargo and could be built cheaply and reused repeatedly. A rocket carries only a small payload, and every launch is costly, delicate, and tightly constrained by timing. What was difficult for wooden ships becomes nearly impossible when the ocean is the vacuum of space. Consider a colony on Mars. Even a population of 100 people would require thousands of kilograms of food each year. Some agriculture might eventually be possible in greenhouses, but the energy and infrastructure needed to grow crops on a hostile planet would be enormous. It could take decades before local production reduced dependence on imports. Until then, rockets would need to deliver continuous shipments of preserved food, seeds, fertilizers, and equipment. If even one resupply mission failed due to weather, mechanical error, or funding shortages, the entire settlement could be pushed toward collapse. Unlike communities on Earth, which can draw support from nearby regions or natural environments, settlers on Mars or the Moon would have no alternatives. Every life support system in space will eventually fail. Pumps, valves, filters, and computer systems all degrade with use. In the unforgiving environment beyond Earth, maintenance is not optional. It is immediate and essential. Many replacement parts are simply too complex to manufacture locally, at least during the early decades of any colony. A failed pump may require metals refined under tightly controlled conditions, or electronics produced with techniques far beyond the capabilities of a small settlement. In those cases, the component must come from Earth. The colony therefore becomes not an independent outpost, but a delicate extension of Earth's supply chain. This vulnerability is already visible aboard the International Space Station. The station hosts only a small crew, yet it relies on one of the most sophisticated logistical systems ever assembled. Regular cargo missions deliver food, water, scientific instruments, and spare parts. Even so, every resupply is planned with care, and any delay creates immediate concern. The station has never been autonomous. It survives through a continuous lifeline to Earth. Expanding this model to support hundreds or thousands of people is almost inconceivable with current technology. Each additional settler increases the logistical load. Flight time, cost, and complexity multiply as more lives depend on supplies traveling through space. The larger the population, the more tightly it is bound to supply lines stretched across immense distances. Every kilogram delivered to orbit carries a high price, and every kilogram sent beyond orbit costs even more. Present launch prices, though decreasing, still reach into the thousands of dollars per kilogram. Even optimistic visions that imagine costs falling below $100 per kilogram face a stubborn reality. A working colony would require millions of kilograms delivered every year. That alone would amount to billions of dollars annually just to keep a small population alive. And this assumes flawless execution, no launch failures, no lost cargo, and no political delays. If even a single critical launch fails, its payload is gone, and the colony feels the impact immediately. Resupplying the Moon is challenging but manageable, with round trips lasting days. Mars is different. Launch windows open only once every 26 months, when Earth and Mars align favorably. This means supplies cannot be sent on demand. They must be planned years ahead. Any emergency arising between windows could be fatal. Imagine an oxygen recycling system failing months before the next launch opportunity. No amount of money or urgency on Earth could overcome the constraints imposed by orbital mechanics. Waste is another factor, often ignored. Colonies will produce vast quantities of it. Worn suits, broken electronics, expired food, and biological refuse. On Earth, waste can be recycled, buried, or dispersed. In space, waste management requires additional systems, each demanding power, maintenance, and spare parts. Recycling is frequently proposed as the answer, but recycling itself consumes energy and machinery, both of which must be supplied and maintained. No recycling loop is perfect. Every cycle loses material. Every machine degrades. Without steady replenishment from Earth, the entire system would eventually fail. Colonists would live with the knowledge that their survival depends on fragile supply lines beyond their control. That awareness creates constant pressure. Life in such a settlement would not feel like freedom. It would feel like existence at the far end of a thin, brittle lifeline stretching across space. The romantic vision of pioneering independence collides with the reality of near-total dependence. This is why logistics, though rarely at the center of space discussions, may be the most decisive factor of all. Building the first habitat may capture attention, but sustaining that habitat year after year requires discipline, infrastructure, and wealth on a scale rarely appreciated. The settlers' lives would be shaped not by dramatic moments of discovery, but by the steady rhythm of deliveries, crates of food, boxes of tools, tanks of oxygen. This is the unglamorous truth. Logistics is the core of survival, and without it, even the most advanced rockets are meaningless. A habitat is not merely a shelter, It is an entire artificial environment carved into an alien world. It must provide air, water, food, power, radiation protection, and medical capability. Each requirement demands equipment, and every piece of equipment adds mass. Even the simplest design expands into staggering tonnage once real needs are counted. Consider the bare minimum, a pressurized living space. On Earth, a modest house might weigh between 50 and 100 tons when structure and fixtures are included. A habitat on the Moon must do far more than a house. It must maintain a breathable atmosphere under pressure while surviving extreme temperature swings between lunar day and night. That requires thick walls, specialized seals, and redundant safety systems. Even using lightweight aerospace materials, a single modest module housing, perhaps 4 astronauts, would weigh several tons before adding furniture, storage, or life support systems. To support even a small permanent crew, multiple modules would be needed, linked together. Suddenly, the living space alone reaches dozens of tons, even in its most stripped-down form. Radiation protection then becomes unavoidable. The Moon has no atmosphere and no magnetic field. Settlers are exposed to cosmic radiation and solar storms that can cause cancer, tissue damage, or acute illness over time. Shielding is essential. Studies have shown that several meters of regolith, the Moon's loose surface material, would be required for long-term protection. That material could be piled over habitats, but the machinery needed to excavate, transport, and place it must first be delivered. Each lunar bulldozer, excavator, or hauler is not a lightweight rover. To move regolith in large quantities, machines must be robust and reliable. On Earth, even compact construction equipment weighs several tons. Sending a single such machine to the Moon could consume an entire heavy lift launch. A working fleet for excavation and shielding could add dozens or even hundreds of tons to the delivery list. Humans also need oxygen, water, and food every day. Recycling systems can extend supplies, but every closed loop loses efficiency over time. A permanent base requires industrial-scale life support, not the limited systems used on the International Space Station. Air scrubbers, water recyclers, and waste processors all include tanks, piping, wiring, and spare components. Each unit is heavy, and redundancy is essential. That means duplicate systems, doubling the mass. Power generation presents another underestimated challenge. On Earth, electricity flows through vast grids. On the Moon, a base must generate all its own power. Solar panels are often suggested, and they can provide energy during the 2-week-long lunar day, but they produce nothing during the equally long lunar night. To survive the darkness, a settlement would need enormous energy storage systems, massive batteries weighing tens of tons, or nuclear reactors. A small modular nuclear reactor capable of powering a base would itself weigh many tons, even before shielding and housing are included. Transporting one safely to the Moon is a formidable engineering task. Transporting several becomes a logistical challenge of extraordinary scale. Even the most basic human comforts rapidly increase the required mass. Beds, clothing, medical supplies, food reserves, exercise equipment, computers, and communication systems all add to the manifest. A medical bay must be capable of handling emergencies, which means surgical instruments, diagnostic devices, and potentially a small operating room. Without such capabilities, a single serious injury could be fatal. As these necessities are counted, the weight grows relentlessly. A realistic calculation for even a minimal base, permanently occupied by a dozen people, quickly rises into the hundreds of tons. Surface rovers, cargo vehicles, and emergency shelters are all essential. Each rover weighs several tons. Each backup habitat or inflatable shelter adds more. A base cannot depend on a single vehicle or structure, because in space, redundancy is survival. With every backup system, the mass multiplies again. The International Space Station, built only for low Earth orbit and not for planetary living, weighs more than 400 tons. That mass was delivered in pieces through dozens of launches. Constructing a permanent lunar base would require a similar or even greater mass, transported over much larger distances and assembled in far harsher conditions. And if the ambition extends beyond survival to growth, families, research, or industry, the requirements expand dramatically. Greenhouses large enough to meaningfully reduce food imports would add hundreds of tons. Workshops for repairing or manufacturing equipment locally would require lathes, foundries, or small fabrication facilities, each far heavier than imagined in a simple concept drawing. A truly permanent base begins to resemble a small town rather than a camp, with mass demands climbing into the thousands of tons. Every ton lifted from Earth demands enormous amounts of fuel. Even with reusable rockets and heavy lift vehicles, the cost in energy and resources is immense. Each launch can carry only a limited load, and every launch requires careful timing and extensive ground support. Delivering the total mass needed for a lunar base would require dozens or perhaps hundreds of missions. Each mission carries the risk of failure. One accident could delay construction for months or longer, leaving half-finished infrastructure stranded on the moon with no way to complete it. This is why realistic estimates for a permanent lunar base often surprise people. What appears small and elegant in an illustration becomes vast when measured in mass. Habitats, shielding, life support systems, power generation, spare parts, medical facilities, vehicles, and redundancies do not add up to tens of tons, but hundreds or thousands. Long before anyone moves in, the base demands a mountain of material to be transported across space. The idea of living off the land carries a powerful romance when applied to space. It evokes images of pioneers building shelters from local materials, growing food in native soil, and crafting tools from what surrounds them. On Earth, settlers could hunt, gather, and farm, reducing dependence on distant supply lines. Applied to the Moon or Mars, this idea becomes deeply appealing. If local dust and rock can be used, perhaps fewer shipments from Earth would be needed. The reality is far more complex. Lunar dust and Martian soil are nothing like the soil on Earth. They are abrasive, sometimes toxic, and far from ready-made resources. Some uses are possible, but most critical needs of a settlement cannot be met this way. Lunar regolith, the fine powder covering the Moon, looks soft in photographs, but under magnification, each grain is sharp, jagged, and glass-like. Unlike Earth's sand, rounded by wind and water, lunar dust was shattered by impacts over billions of years. It clings to surfaces through static charge, scratches metal, and can damage human lungs if inhaled. Despite these hazards, regolith does contain useful minerals. It holds silicon, aluminum, iron, calcium, and trace elements. In principle, it can be melted into bricks or fused into concrete-like blocks. Experiments on Earth have shown that heating regolith simulants with microwaves or concentrated sunlight can bind the grains into solid slabs. These slabs could serve as radiation shielding or landing surfaces. In that sense, the dust has promise. But the limits are severe. Turning regolith into building material requires enormous energy. Melting or fusing even small amounts means heating it to thousands of degrees Celsius. On the Moon, where power is scarce, producing such heat at industrial scale would be extremely difficult. It might work for rough structures like walls or shields that do not require precision, but not for complex machinery. You cannot fabricate valves or circuit boards from raw lunar dust. For life support systems, electronics, and medical devices, supplies from Earth remain essential. Martian soil presents a different challenge. At first glance, Mars appears more favorable. Its soil contains iron oxides, which give the planet its red color, along with other minerals. More importantly, Mars holds frozen water in its ground, a resource far more valuable than metal. By heating or processing the soil, water could be extracted for drinking, oxygen production, or even fuel. Experiments have already demonstrated small devices that convert carbon dioxide from the Martian atmosphere into oxygen. Scaling this to support human life remains distant, but the basic ingredients exist. Yet Martian soil is also hazardous. It contains perchlorates, salts that are harmful to humans. Handling it safely would require careful processing to avoid poisoning settlers or contaminating crops. The notion of planting seeds directly into Martian soil is unrealistic without extensive treatment. Even after detoxification, the soil lacks many nutrients plants require. Agriculture would still depend on importing fertilizers or producing them through energy-intensive chemical processes. Living off the land would not mean living directly from the soil, but transforming it through sophisticated engineering. Fuel production offers some possibilities, but again, with limits. Lunar regolith contains oxygen bound within minerals. Through chemical reduction, that oxygen can be released. Oxygen is vital for breathing and as an oxidizer for rocket propellant. The difficulty lies in scale. Extracting oxygen requires heavy processing equipment and continuous energy input. Establishing such systems would itself require large shipments from Earth. Mars is better positioned in this respect. Its carbon dioxide atmosphere can be used to produce methane and oxygen propellants through chemical reactions. But the machinery to perform these processes, store the fuel, and maintain operations would all need to be delivered first. Local manufacturing also collides with the limits of precision. Even if metals can be extracted from dust or rock, refining them to aerospace quality is extraordinarily complex. On Earth, steel production relies on massive furnaces, precise chemistry, and extensive supply chains. Aluminum, titanium, and other lightweight metals demand huge amounts of electricity and advanced processing. Producing them on the Moon or Mars is not impossible, but the infrastructure required resembles that of an industrial city rather than a small outpost. Expecting early settlers to build such industry from scratch is unrealistic. For decades, any equipment requiring high precision, from engines to electronics to medical devices, would still need to come from Earth. Three-dimensional printing is often proposed as a solution. In theory, local dust could be turned into printer feedstock, allowing parts to be fabricated on site. Experiments have shown that regolith simulants can be bound into simple shapes, but there is a vast gap between printing a basic block and producing a complex load-bearing engine component. Printers capable of such precision require carefully prepared materials, advanced nozzles, and sophisticated software. They are also prone to failure and would themselves depend on imported spare parts. In practice, printing might help with non-critical items like tiles or structural panels, but it cannot replace Earth's industrial base. On Mars, the presence of water ice suggests that greenhouses could eventually operate. On the Moon, the lack of atmosphere and liquid water makes agriculture even more challenging, though hydroponic systems are possible if water can be efficiently recycled. In both cases, large habitats, artificial lighting, fertilizers, and constant maintenance are required. Producing enough food to reliably feed even a dozen people would demand facilities weighing dozens of tons, along with continuous inputs. The idea of settlers simply growing crops in alien soil ignores the fact that Earth's soil is the result of billions of years of biological activity. Without that hidden complexity, soil is little more than sterile dust. In space or on another world, every one of those natural processes must be recreated artificially, and none of it comes without cost. The first obstacle is light. On Earth, the sun provides a steady flow of energy, softened by the atmosphere in a way that sustains life. On the Moon, there are 2 weeks of continuous daylight, followed by 2 weeks of complete darkness. A greenhouse placed there would either overheat under constant sunlight or freeze during the endless night. On Mars, the day and night cycle is closer to Earth's, but the sunlight is far weaker, at about 43% of what we receive here. That makes artificial lighting essential, powered by electricity from solar panels, nuclear reactors, or other energy sources. A simple act, like photosynthesis, suddenly depends on a chain of machines and power systems. Water presents another challenge. On Earth, rain circulates through the atmosphere and returns to the soil almost effortlessly. In space, every drop must be delivered or recycled. A single tomato plant might require 2 liters of water each week. Multiply that by hundreds or thousands of plants, and the quantities grow rapidly. Recycling systems can recover some water through condensation, but no system is perfect. Water is lost through leaks, evaporation, or absorption into growing media that eventually must be replaced. Scientists have shown that plants can grow in hydroponic or aeroponic systems with careful recycling, but scaling these systems to feed an entire crew or colony would require constant attention and a steady supply of replacement parts. Then there are nutrients. Plants cannot survive on light and water alone. They need nitrogen, potassium, phosphorus, and many trace minerals. On Earth, these are supplied naturally by soil ecosystems, supported by bacteria, fungi, and decomposing organic matter. On the Moon or Mars, there is no soil in this sense, only dust and rock with little biological activity. Fertilizers would need to be shipped from Earth, manufactured locally through complex chemical processes, or endlessly recycled from human and plant waste. Each option has serious limitations. Importing nutrients is expensive and unsustainable. Manufacturing them requires heavy machinery and large amounts of energy. Recycling has limits. Without a stable nutrient supply, crops weaken, yields decline, and the food system eventually fails. On Earth, the atmosphere and magnetic field shield plants from high-energy radiation. In space, radiation can damage plant DNA, slow growth, and reduce productivity. Greenhouses can be shielded with thick layers of soil or water, but that adds enormous mass. Another option is to grow plants underground using artificial light, but that returns us to the problem of energy. The more protection crops need, the more power is required to keep them alive. Humans also need a balanced diet: calories, protein, fats, vitamins, and minerals. Growing just one or two hardy crops is not enough. A colony would need a wide variety of plants, grains for carbohydrates, legumes for protein, fruits and vegetables for vitamins, and oils for fats. Each crop has specific needs for light, water, and nutrients, adding further complexity. On Earth, agriculture depends on vast fields, specialized machinery, pollinators such as bees, and centuries of selective breeding. Recreating even a small fraction of this system inside a habitat is an enormous challenge. A laboratory experiment or a space station test can show that lettuce or radishes will grow, but feeding 10 people continuously requires hundreds of square meters of growing space. Feeding 100 people requires thousands. Every square meter demands lighting, water delivery, air circulation, and temperature control. On Earth, a poor harvest in one region can be offset by imports from another. In space, failure could mean starvation. Some researchers suggest supplementing crops with algae or single-cell proteins. Algae can grow rapidly in small volumes of water, and microbial protein can be produced in bioreactors. These methods could provide essential nutrients, but they fall far short of the comforting image of fields and orchards. A diet dominated by algae or microbial paste might meet calorie needs, but it would offer little psychological comfort. Food is deeply tied to culture and morale, not just survival. Life in isolation would be harder if meals became monotonous and joyless. Pollination introduces another difficulty. Many crops rely on insects. Recreating this system away from Earth would require importing insects, which poses ecological risks, or developing mechanical pollination systems. Hand pollination is possible, but extremely labor-intensive and impractical at scale. Without reliable pollination, many staple crops cannot reproduce effectively. Food storage and safety add yet another layer of complexity. On Earth, refrigeration, preservation methods, and global trade networks ensure food availability even when local production fails. Away from Earth, storage capacity would be limited, and every gram of food would matter. If a harvest became contaminated by mold or bacteria, the loss could be catastrophic. Preventing contamination, managing waste, and maintaining hygiene would require constant vigilance. For now, space agencies rely on packaged food shipped from Earth, carefully designed to meet nutritional needs. But this approach does not scale well. As the number of people in space increases, so does the mass of food that must be launched. The food challenge is not simply about growing plants. It is about recreating an entire biosphere in miniature, something humanity has never fully achieved. Energy underpins every one of these systems. It powers heating, cooling, air circulation, water recycling, communication, and food production. Without energy, even the most advanced life support systems fail within hours or days. The Moon and Mars are not rich in easily accessible power. They are power deserts. Unlike Earth, which rotates every 24 hours, the Moon rotates once every 29.5 days. This creates a lunar day lasting about 2 weeks, followed by a lunar night of equal length. During daylight, solar panels can collect abundant energy. When night falls, temperatures drop below -170 degrees Celsius, and darkness is complete. Surviving this period requires storing enormous amounts of energy or relying on another source entirely. Storing 2 weeks of power at the scale needed for a base is beyond the capability of current battery technology. Small modular nuclear reactors could provide continuous power, regardless of day or night. But these systems are heavy, complex, and politically sensitive. Launching one safely from Earth requires extreme precautions. Once on the Moon, it would need shielding, cooling systems, and trained operators. Reactors also have limited lifespans, and replacement components would still have to come from Earth. Nuclear power could support lunar operations, but it is not a simple solution. Mars offers a different challenge. A Martian day lasts about 24.6 hours, close to Earth's rhythm. However, sunlight there is only about 43% as strong as on Earth. Dust in the atmosphere reduces it further, and global dust storms can last for weeks or even months, blocking much of the sunday. Solar panels that perform well in clear conditions may suddenly produce only a fraction of their output. A settlement relying on solar energy alone would need vast panel arrays and massive energy storage to survive storm seasons. Mars is also cold, with average surface temperatures around -60 degrees Celsius. Habitats must be constantly heated to protect both people and machinery. Heating requires uninterrupted power, even during storms or long nights. On the Moon, the challenge is even greater during the 2-week-long night, when every watt of heat consumes precious stored energy. Wind power is sometimes proposed for Mars, but the thin atmosphere makes it ineffective. Although Martian winds can be fast, the air density is only about 1% of Earth's. Even powerful storms exert less force than a gentle breeze on Earth. Wind turbines would generate little usable energy. Geothermal power, which supports some systems on Earth, is uncertain on the Moon or Mars. Mars shows signs of ancient volcanism, but near-surface heat is weak, and drilling in such environments would be extremely difficult. All of this points to a stark reality. Energy, more than distance, may be the greatest barrier to sustainable colonies. On Earth, power systems are supported by vast infrastructures, grids, pipelines, refineries, and repair crews. Beyond Earth, there is no backup. Every system must be self-sufficient, redundant, and durable enough to function without outside help for long periods. Building such systems is far harder than placing solar panels on alien ground. On Earth, power lines stretch hundreds of miles. On the Moon or Mars, cables must be insulated, buried, or shielded against radiation, dust, and extreme temperatures. Solar farms might need to be located kilometers from habitats, increasing transmission losses and infrastructure demands. Every meter of cable or pipe must be delivered, installed, or manufactured, adding to the burden. Some proposals suggest orbiting solar stations that beam energy down using microwaves or lasers. In theory, such systems could avoid long nights and storms by remaining in constant sunlight. In practice, the technology is unproven at the required scale, and energy losses during transmission are significant. Building and maintaining these stations would itself be a monumental task. Others propose combining multiple small reactors with solar systems to provide redundancy. Even then, spare parts, skilled technicians, and maintenance schedules would still depend on Earth. Energy is the pulse that drives every other system, and the Moon and Mars are worlds that resist it at every turn. Power there is scarce, fragile, and difficult to sustain. It must be forced into existence through enormous effort. Despite decades of progress in spaceflight and robotics, large-scale manufacturing beyond Earth remains more illusion than reality. On Earth, industry flourishes within a dense network of resources, infrastructure, and skilled labor. Raw materials are mined, refined, and processed in specialized facilities before reaching factories that depend on reliable power, logistics, and human expertise. Components are produced in many different locations and then brought together for assembly. Global supply chains allow industries to specialize efficiently. A smartphone, for instance, depends on glass manufactured in one country, chips fabricated in another, and metals mined somewhere else entirely. All of this coordination involves millions of people and vast networks of machines. Now imagine removing that entire system and attempting to recreate it on a barren planet or in orbit, with only a small crew and a limited set of tools. So far, manufacturing experiments in space have been modest. A handful of three-dimensional printers have been tested aboard the International Space Station, producing small plastic objects such as tools or simple brackets. These trials showed that additive manufacturing can function in microgravity and can be useful in emergencies. Yet the printers still rely on feedstock, plastic filament, that must be launched from Earth. They also produce only small, simple items. Metal printing is far more demanding. It requires very high temperatures and precise control over material properties. Even on Earth, where conditions are stable, producing high-quality metal parts through printing is a specialized process requiring advanced facilities. Manufacturing on Earth depends on extreme precision. Machines are calibrated to exact tolerances so that components fit perfectly. Dust, vibration, or small temperature shifts can ruin an entire production run. On the Moon or Mars, the environment actively works against precision. Dust clings to surfaces, temperatures fluctuate wildly, and radiation interferes with electronics. Machinery can be protected inside sealed habitats, but that consumes valuable pressurized space and demands life support, not only for people, but for machines as well. Manufacturing also consumes enormous amounts of power. Smelting metals, for example, requires sustained high heat. On Earth, this is supplied by massive furnaces powered by coal, natural gas, or extensive electrical grids. A single industrial process could require more energy than an entire off-world settlement could generate, making large-scale manufacturing impractical with current technology. Building complex machines also requires access to a wide range of elements: iron, copper, aluminum, silicon, rare earth elements, and more. Earth's industries draw from an entire planet's worth of resources. The Moon contains some useful materials, but they are dispersed and difficult to extract. Mars may offer a broader mix, but mining and refining them would require heavy equipment, chemical processing plants, and skilled labor. Mining is not simply a matter of digging up soil. Ores must be crushed, processed, and chemically treated before becoming usable metal. Each step requires its own machinery and chemicals, which themselves must be produced. It is a chain of dependency that cannot be easily established on another world. Even if raw materials could be obtained, turning them into advanced products is a further leap. Producing a simple steel beam or aluminum sheet might one day be possible. But manufacturing a rocket engine, a solar panel, or a reliable circuit board involves dozens of specialized processes. A single microchip, for example, requires facilities cleaner than an operating theater, with tools that etch structures smaller than a virus. These factories cost billions of dollars to build on Earth and depend on global supply chains. Recreating them on the Moon or Mars lies far beyond current capability. Some argue that advanced automation could solve the labor problem. Robots could, in theory, handle mining, refining, and manufacturing without needing air or food. But robots are not independent workers. They are tools designed for specific tasks. Even on Earth, automated factories rely on large teams of technicians and engineers to maintain equipment, diagnose failures, and adapt processes. In space, robots would need to function without such dense support. They would also need a level of flexibility and autonomy far beyond what exists today, able to handle unfamiliar problems without constant human guidance. That capability is still under development. The logistics of establishing even a single factory are overwhelming. On Earth, heavy machinery can be transported by road, rail, or sea. An industrial furnace alone can weigh tens of tons. Even with modular designs, the number of rocket launches required to deliver such equipment would be enormous. The cost of transporting the first factory might exceed the cost of resupplying a settlement from Earth for decades. For now, the most realistic vision of manufacturing beyond Earth is limited to support functions. Small-scale production of replacement parts, simple tools, or basic structural components could reduce dependence on Earth. Printing a spare wrench or bracket might save a mission. Producing construction materials such as bricks from lunar dust or Martian soil is being studied and could help build habitats. But these are narrow, specialized activities, not full industrial systems. They extend supplies but do not remove the need for Earth-based support. The broader vision of space cities manufacturing their own rockets, electronics, and machinery remains distant. Achieving it would require breakthroughs not only in manufacturing, but also in energy production, robotics, and materials science. More importantly, it would require an economic system in space capable of supporting such industry. Manufacturing thrives where there are markets, workers, and demand. For now, those conditions exist only on Earth. High-technology life support systems already depend heavily on redundancy. Spacecraft and stations carry backups for nearly everything. The International Space Station has multiple oxygen generation systems, several methods for removing carbon dioxide, and manual emergency options in case automation fails. But redundancy adds mass. An extra carbon dioxide scrubber may weigh several hundred kilograms. Additional oxygen tanks add hundreds more. Duplicating an entire system can double its mass. For short missions, this is manageable. For permanent settlements, redundancy becomes overwhelming. A base designed for a dozen people may require not just one or two backups, but entire parallel systems ready to take over when others fail. Repair adds another layer of complexity. Spare parts must be stored, and specialized tools must be available. Every component has its own maintenance schedule. On Earth, repairs are supported by extensive supply chains, skilled technicians, and factories producing replacement parts. Away from Earth, those networks do not exist. If a specialized pump fails on Mars, the choices are limited. Either a replacement is already available, or the crew must improvise using whatever tools and materials they have. Both options are difficult. Carrying spares for every component quickly inflates cargo mass beyond practicality. Apollo missions included backup oxygen systems and manual procedures for re-entry. The space shuttle used multiple computers operating in parallel, constantly checking one another. Crews aboard the International Space Station spend much of their time maintaining and repairing life support. Even with frequent resupply from Earth, failures are common. Fans break, valves clog, water recycling systems fail. Each problem requires hours of work and often waiting for spare parts on the next cargo mission. Now imagine the same situation at a base that cannot depend on rapid resupply. The fragility becomes clear. Every kilogram of spare parts replaces a kilogram of food, water, scientific equipment, or construction material. Planners must decide which systems deserve full duplication and which must accept greater risk. Every compromise increases the chance that a series of unlucky failures could cascade into disaster. Astronauts are trained broadly, but they cannot be experts in every specialized system. Repairing a pump may require knowledge of fluid mechanics, electronics, and machining. On Earth, a team of specialists would handle the task. In space, the crew must improvise, often under extreme pressure. Training for every possible failure is impossible. Crews rely on guidance from Earth, but on Mars that guidance is delayed by up to 20 minutes each way. Real-time problem-solving becomes slow and fragmented, while systems may already be nearing collapse. A life support system might have several backups, but if they all draw power from the same source, a power failure disables them all. True redundancy demands independent systems, separate power supplies, separate storage, and sometimes separate habitats. That multiplies the scale again. Instead of one module, two may be required, each with full life support. Instead of one power system, two must be built. Each added layer of safety dramatically increases mass, complexity, and cost. High-technology life support is not a single elegant system that runs indefinitely. It is layered, fragile, and constantly demanding attention. Closed-loop systems are often described as the ultimate goal for space settlement. The idea is compelling. Rather than shipping water, food, and oxygen across millions of kilometers, everything is reused. Waste becomes input. Resources circulate endlessly, and nothing is lost. On Earth, this happens naturally through the biosphere. The carbon dioxide you exhale feeds plants. Water cycles through clouds and rivers. Nutrients move through soils, oceans, and living organisms. The planet performs this work silently. In orbit, on the Moon, or on Mars, there is no such invisible machinery. Every molecule must be monitored, processed, and reused by machines or tightly managed ecosystems. Humans produce carbon dioxide, salts, and organic waste. All of it must be converted back into safe, usable forms. Plants can absorb some of it, but they also create waste and require precise conditions. Machines can filter gases, distill water, and capture carbon, but they are never perfect. On Earth, losses vanish into the background of a vast biosphere that constantly restores balance. In space, every gram of oxygen or nitrogen that escapes is gone forever unless it is replaced. Over months and years, even the smallest inefficiencies accumulate. This is why the vision of a perfectly closed system remains largely an engineering aspiration rather than a reality. Experiments have attempted to test this idea. One of the most well-known was Biosphere 2 Inches Arizona, constructed in the late 1980 seconds. The aim was to seal 8 people inside a massive dome filled with plants, animals, and carefully designed ecosystems. The system was meant to operate for 2 years without outside supplies, recycling everything internally. The results were, at best, mixed. Oxygen levels dropped to dangerous lows, eventually forcing outside intervention. Nutrient balances shifted in unexpected ways, allowing some organisms to dominate while others declined. Microbes in the soil consumed far more oxygen than predicted, destabilizing the entire environment. The experiment did not completely fail. People survived, crops grew, and recycling functioned to a degree, but it revealed just how intricate Earth's biosphere is, and how difficult it is to reproduce even a small fragment of it. The International Space Station relies heavily on recycling. Astronauts drink water reclaimed from urine, humidity, and other waste streams. Carbon dioxide is removed from the air using chemical scrubbers, and oxygen is sometimes produced by splitting water molecules through electrolysis. Yet even after decades of refinement, the station does not operate as a fully closed system. Cargo vehicles regularly deliver water, oxygen, and food. Recycling reduces dependence, but it does not remove it. Over long timescales, the unknowns grow. Plastic tubing exposed to radiation becomes brittle. Metals fatigue and corrode under repeated stress. On Earth, a broken part is replaced. In a truly closed loop, every replacement would need to be made from within the system itself. That implies access to raw materials, processing equipment, and fabrication tools, all of which also require maintenance. A closed loop is not only about recycling air and water, it is about recycling the machinery that performs the recycling. This recursive demand rapidly becomes overwhelming. Plants themselves are complex living systems. They are sensitive to light, nutrients, humidity, and pollination. Over time, crops can fail due to disease, genetic drift, or subtle environmental imbalances. On Earth, farmers can intervene, adjusting soil chemistry, introducing predators, or bringing in new seeds from outside. Inside a sealed habitat on Mars or the Moon, those options are limited or non-existent. A single fungal outbreak could destroy an entire harvest. That risk demands redundancy, multiple crops, backup seeds, and additional lighting systems. Microbial communities, often ignored, are equally critical. On Earth, soil microbes convert waste into nutrients usable by plants. In artificial environments, their behavior can be unpredictable. Some consume oxygen, as happened in Biosphere 2, or produce harmful byproducts. Others may evolve under unusual conditions, altering their role in the ecosystem. A biologically based closed loop is not static. It changes, sometimes in unstable ways. Managing it requires constant monitoring and intervention, a heavy burden for a small crew already stretched thin. Engineers often argue for purely mechanical solutions: filters, scrubbers, chemical reactors. These systems can be designed, modeled, and duplicated. But machines also degrade. Catalysts lose effectiveness. Bearings wear down. The idea of machines that recycle endlessly without maintenance ignores basic material limits. Radiation, thermal cycling, and abrasive dust in space accelerate wear rather than slow it. Systems that function for a handful of astronauts in orbit may not scale to dozens or hundreds of settlers on Mars. Larger populations mean more waste, more air to manage, and more food to produce. Processes that are stable at small scale can become unstable when expanded. Tiny inefficiencies multiply as the loop grows. This uncertainty makes the prospect of fully self-sustaining colonies unclear. What works in a laboratory chamber or a space station module may fail in a city-sized habitat. Some researchers advocate hybrid approaches, partial recycling supplemented by external supply. Oxygen might be mostly recycled but occasionally replenished through local production from electrolysis of lunar ice. Food could be grown partly on site, with regular imports filling the gaps. These ideas are less ambitious, but far more realistic. A perfectly closed loop has not yet been achieved and may never support large populations. Humans have always lived in open systems, able to step outside for fresh air or gather resources from the environment. In a closed loop, every action affects stability. Using extra water, mishandling waste, or altering light levels in a greenhouse can ripple through the system. This constant fragility could weigh heavily on settlers, turning daily life into an exercise in maintenance rather than exploration. Living inside a system that must function flawlessly at all times could change how people think about freedom, community, and survival. Closed-loop research will continue because the alternatives are equally daunting. Progress will likely be incremental: better water recovery, more reliable carbon removal, and more resilient crops. But the leap from partial recycling to true autonomy remains unexplored. We do not yet know whether a system can run for decades without outside input. If such a system ever exists, it may resemble a patchwork of overlapping processes rather than a neat, perfect loop. Radiation presents another barrier, largely invisible but ever-present. There are two primary sources of radiation in space. One comes from our own star. The Sun constantly emits streams of charged particles, known as the solar wind. Most of the time, this radiation is mild. But occasionally, the Sun erupts. During solar storms, immense clouds of energetic particles are hurled outward, reaching Earth within hours. When they strike satellites, they can destroy electronics. When they strike unprotected humans, the exposure can be deadly. Astronauts caught outside during a major solar event would need to reach shielded areas quickly or risk severe radiation sickness within hours. The second source is even more challenging: galactic cosmic rays. These are high-energy particles, often protons or atomic nuclei, accelerated to near light speed by distant supernovae and black holes. They arrive from all directions and cannot be predicted or avoided. Shielding against them is a matter of mass and physics. Radiation can be blocked, but only by placing sufficient material between the source and the person. On Earth, this is effortless. We are protected by kilometers of atmosphere and rock above our heads. In space, achieving that level of protection is almost impossible. Every kilogram of shielding must be launched at enormous expense. To give astronauts the same protection they enjoy on Earth would require walls several meters thick, made of water, concrete, or metal. Such structures are impractical. Engineers are forced to compromise, using thinner layers of aluminum or specialized plastics to reduce exposure. These measures help, but they cannot remove the danger entirely. Aboard the International Space Station, astronauts receive radiation doses hundreds of times higher than people on the surface of Earth. These levels are not immediately lethal, but over time they raise the risk of cancer, cataracts, and damage to the nervous system. Missions lasting 6 months already approach recommended safety limits. A journey to Mars and back, lasting 2 to 3 years, would expose crews to far greater doses. Without sufficient shielding, the voyage itself could shorten lives or leave survivors with long-term health problems. The Moon presents an even harsher environment in some ways. With no atmosphere and no magnetic field, the lunar surface is directly exposed to space radiation. During the Apollo missions, astronauts were fortunate that no major solar storms occurred while they were on the surface. A single powerful event could have been fatal. Various shielding strategies have been explored, but each comes with drawbacks. Thick metal walls seem like an obvious solution, yet metals can produce secondary radiation when struck by cosmic rays, sometimes worsening exposure. Plastics rich in hydrogen atoms perform better, as hydrogen absorbs charged particles with less secondary radiation. Water is also highly effective, and some designs propose surrounding living quarters with water tanks. In theory, fuel, water, and other consumables could be arranged to serve as shielding, but again, mass is the limiting factor. Every additional ton of water or plastic makes launch more difficult and far more costly. One option for settlements is to pile regolith on top of habitats, creating a natural barrier. Several meters of regolith would significantly reduce radiation exposure, but implementing this is far from simple. Moving and stacking large volumes of soil requires heavy machinery, energy, and time. Until such shielding is completed, settlers would remain exposed. Early crews would need temporary measures. Some researchers have proposed magnetic or electric shields, designed to mimic Earth's magnetic field on a smaller scale. The concept is to create a charged bubble that deflects incoming particles. In principle, such a system could protect a spacecraft without massive physical shielding. In practice, generating and sustaining a field strong enough is well beyond current capabilities. The required fields would be enormous, consuming vast amounts of energy and potentially interfering with electronics or even affecting the crew. For now, these ideas remain theoretical, more suited to academic papers than real missions. Radiation damage also carries a deep uncertainty. Short-term effects, such as radiation sickness, are well understood. The long-term impact of continuous low-dose exposure in space is far less clear. On Earth, data comes from radiation workers, medical patients, and survivors of nuclear accidents. But these situations do not perfectly match the space environment. Cosmic rays, for example, are far more energetic than most radiation encountered on Earth. They can penetrate deeply into tissue, causing clustered DNA damage that cells struggle to repair. This makes predictions difficult. Are the risks acceptable for missions lasting several years, or would gradual exposure degrade physical and cognitive function over time? The answer remains unknown. For space settlements, this uncertainty is critical. A colony on Mars or the Moon would not only include healthy adults, but potentially children. Developing bodies are far more sensitive to radiation. Generations raised under elevated cosmic radiation could face higher cancer rates, genetic damage, or developmental problems. Shielding may reduce these risks, but unless it approaches the effectiveness of Earth's natural protection, the long-term health of such populations is uncertain. Unlike fires or mechanical failures, radiation offers no warning alarms and no quick fixes. The threat is silent and constant. People might learn to live with it, just as early sailors accepted storms and disease, but it may also severely limit long-term habitation unless true solutions are found. Without protection from the constant rain of particles in space, every other system becomes secondary. Settlers might have food, air, and power, yet still age faster, fall ill more often, and gamble with invisible forces. Low gravity introduces another slow but profound form of damage, affecting bones, brains, and blood. In footage from the Apollo missions, astronauts appear to hop and glide as if gravity's rules had softened. Beneath that light-hearted motion lies a serious biological challenge. Human bodies evolved under one constant gravitational pull. Muscles, bones, and even circulation are tuned to Earth's gravity. Reduce or remove that pull, and bodily systems begin to change in ways that are not immediately visible but are deeply harmful over time. Bones are among the first to suffer. On Earth, every step loads the skeleton, keeping bones dense and strong. Gravity acts as a continual stimulus, forcing bones to maintain their structure. In orbit, or on the Moon where gravity is only 1/6 of Earth's, or on Mars with about 1/3, that stimulus is greatly reduced. The body adapts, but in the wrong direction. Without regular stress, bones lose minerals. Calcium leaches into the bloodstream, leaving bones weaker and more prone to fracture. Measurements from astronauts show losses of 1 to 2% of bone mass per month in weight-bearing regions such as the hips and legs. This rate is far faster than osteoporosis on Earth, which typically develops over decades. Over long missions, the consequences become severe. A year in space can reduce bone density by more than 10%, enough to make simple falls dangerous. Muscles follow a similar decline. On Earth, standing, walking, and lifting all require effort. In microgravity, floating requires almost none. Even in the partial gravity of the Moon or Mars, everyday movements demand far less work than our bodies are designed for. Muscles respond by shrinking, strength decreases, endurance fades, and coordination deteriorates. On the International Space Station, astronauts spend hours each day exercising with resistance devices, treadmills, and stationary bicycles. These routines slow the decline but do not prevent it. After 6 months, returning astronauts often need weeks to regain strength and balance. In a settlement where people might live for years or even their entire lives in low gravity, the long-term outcome is unknown. Will muscles adapt in a stable way or remain permanently weakened? No one yet knows. Gravity also governs how fluids move inside the body. On Earth, blood and other fluids are pulled downward, pooling in the legs and feet. In orbit, fluids shift upward toward the chest and head. Faces swell, sinuses fill, and legs thin. This redistribution may look cosmetic, but it places strain on sensitive systems. Some astronauts have experienced lasting vision problems, thought to result from increased pressure inside the skull. This condition, known as spaceflight-associated neuroocular syndrome, suggests that the brain and eyes are not built to function without gravity's influence. On the Moon or Mars, where gravity is weaker but not absent, the effect may fall somewhere between Earth and orbit. How damaging that might be over years or decades remains an open question. The heart, no longer required to work as hard to push blood against gravity, begins to lose strength. Cardiac muscle shrinks, and overall blood volume decreases. When astronauts return to Earth, many feel dizzy or even faint when standing, because their hearts and blood vessels have forgotten how to respond to gravity. On the Moon or Mars, settlers would not be returning home quickly. They would live in a permanent in-between state, where circulation never fully adapts in either direction. What this means for long-term cardiovascular health is still uncertain, but the danger is real. The brain may also be affected. Research shows that time spent in microgravity alters brain structure. Magnetic resonance imaging scans taken before and after missions reveal shifts in both grey matter and white matter. Some regions expand, others contract. The full significance of these changes is not yet understood, but the possibility that reduced gravity could impair cognition, memory, or motor control raises serious concern. If settlers must make critical decisions under pressure, even subtle cognitive decline could become life-threatening. Small impairments, accumulated over time, could steadily erode mission safety. The International Space Station has become a laboratory for studying these effects. Most astronauts stay for 6 months. A small number have remained close to 1 year. Even within this relatively short duration, bone loss, muscle atrophy, cardiovascular weakening, and vision problems appear. Longer exposures have not yet been studied in humans. A mission to Mars would require at least 2 to 3 years, including time in microgravity during transit and partial gravity on the surface. Permanent colonies would mean entire lifetimes spent away from Earth's pull. The experiment has barely begun, and the early signals are worrying. If humans were to raise families on Mars or the Moon, children would develop from birth under reduced gravity. Bones might never reach Earth normal density. Muscles could remain smaller. Hearts might grow weaker. Cognitive development could be influenced by fluid shifts and altered brain structure. No one can say with certainty how severe these effects would be, but they could make returning to Earth impossible for those born in low gravity. Over generations, settlers might diverge into a distinct branch of humanity, adapted to weaker worlds, but too fragile for the one their ancestors came from. Countermeasures have been suggested, but none are straightforward. Exercise equipment can slow bone and muscle loss, but it requires time, discipline, and bulky machinery. It cannot truly replace the constant force of gravity. Artificial gravity, produced by spinning spacecraft or rotating habitats, is often proposed as a solution. In theory, rotation could simulate gravity through centrifugal force. In practice, building and safely operating large rotating structures is an immense engineering challenge, far beyond anything constructed so far. Smaller rotating sections might offer partial relief, but they introduce significant technical and financial complications. On planetary surfaces, gravity cannot be altered. Mars will always have about 1/3 of Earth's gravity, the Moon about 1/6. The only options are to adapt or to build rotating habitats separate from the surface. Adaptation is possible, but it may come at a cost. The human body is resilient, yet it has limits. Excessive bone loss, muscle weakness, and fluid imbalance lead to disease. Even if settlers accept physical frailty as the price of life on another world, they must still be strong enough to survive harsh conditions, operate heavy machinery, and respond to emergencies. Weakness could mean the difference between repairing a failing system in time or losing an entire habitat. A functioning community cannot rely on people who are too fragile to perform demanding physical tasks. Reproduction and childhood beyond Earth introduce even deeper uncertainty. No human has ever conceived or given birth in space. The question has barely been explored even in animals. Some experiments have flown small mammals, insects, and fish, but most were short-term and incomplete. In certain cases, fertilized eggs developed normally for a while. In others, embryos failed to develop properly or showed abnormalities. None of these studies answers the central question of what happens when a full mammalian reproductive cycle, especially a human one, takes place away from Earth. On our planet, reproduction and pregnancy depend on finely balanced biological processes. Cells divide, embryos implant, organs form, and the body supports growth over many months. All of this evolved under one constant gravity. Reduce or remove that force, and it is unclear whether these processes will proceed normally. For example, fertilized eggs must travel through fallopian tubes, guided by microscopic hair-like structures and fluid motion. Gravity likely contributes to this movement. Without it, the journey could be disrupted, leading to failed implantation or abnormal development. Even if implantation occurs, pregnancy places heavy demands on the body. Circulation, bone health, and nutrient delivery are all under strain. On Earth, the body compensates. In space, fluids shift toward the head, bone density declines, and blood volume drops. Would a pregnant body in microgravity be able to deliver sufficient oxygen and nutrients to a developing fetus? Would reduced gravity alter how organs form, how bones grow, or how the brain develops? These are not abstract questions. They lie at the core of whether humans can truly become a spacefaring species. If conception and pregnancy occur under 1/6 or 1/3 of Earth's gravity, development may diverge from the very beginning. Bone formation could be weaker, muscle growth slower, and the positioning of organs altered. What would emerge is unknown because it has never been tested, but there is a real possibility that children born on Mars or the Moon would differ fundamentally in physiology. They might thrive under their native gravity yet struggle or even fail to survive if brought to Earth later. Developing embryos are especially vulnerable to damage to their genetic material. On Earth, radiation exposure during pregnancy is carefully limited. Doctors advise against X-rays and urge caution, even with relatively small risks. In space, exposure is constant and unavoidable. For an embryo, this could result in miscarriage, birth defects, or delayed development. Even if pregnancy reached full term, the long-term risk of childhood cancer or genetic instability would likely be elevated. The growth of bones, muscles, and organs depends on load and stress. On Earth, children strengthen their skeletons as they crawl, walk, and run under full gravity. On Mars or the Moon, body weight is lower and the mechanical challenge is reduced. The outcome could be bones that never achieve Earth-level density. Muscles might remain smaller and cardiovascular systems less resilient. Over generations, a population could emerge that is unable to safely visit or return to Earth, effectively confined to its planetary birthplace. The brain develops rapidly during childhood, shaped by both biology and environment. If low gravity causes fluid shifts that increase pressure inside the skull, as seen in adults, what would that mean for a developing brain? Could memory, learning, or behavior be altered? The social environment would also be unprecedented. Growing up inside confined habitats, under artificial lighting, surrounded by machines, and a very small community, would be profoundly different from childhood on Earth. Isolation, the absence of natural landscapes, and constant awareness of danger could shape culture and psychology in ways we cannot yet foresee. Studying reproduction in space raises serious ethical questions. Sending animals is controversial, and involving humans even more so. The risks are high and the unknowns vast. No organization has yet attempted human conception beyond Earth, largely because of these moral barriers. Yet without such knowledge, the vision of long-term settlement remains incomplete. A colony cannot rely forever on adults imported from Earth. Eventually, birth and childhood must occur, or the settlement will vanish when its first generation ages and dies. Some possible solutions have been suggested. Artificial gravity could provide conditions closer to Earth for pregnancy and development. A rotating nursery might protect children from the most severe effects of low gravity during critical stages of growth. Nutritional strategies, exercise programs, and intensive medical monitoring might reduce other risks. But these ideas remain partial and untested. The deeper reality is that we do not yet know whether humans can safely reproduce away from Earth. The common assumption that settlers on Mars will naturally form families and build a thriving society rests on optimism rather than evidence. It assumes that biology will adapt smoothly, that evolution's finely balanced processes will continue under alien conditions. Until experiments are carried out, these remain assumptions, and the balance of evidence points toward difficulty rather than ease. The human body is an interconnected system, and disturbing one element can cascade through development in unpredictable ways. On one side, we possess the technical capability to launch rockets, construct habitats, and perhaps keep adults alive for years on Mars or the Moon. On the other, we lack even basic knowledge of whether those adults could ever raise children there. It is as though we have learned how to build a house, but do not know whether the neighborhood contains air, water, or fire. Without that understanding, the idea of becoming a multi-planet species remains unfinished. The image of children playing beneath a pale Martian sky or leaping lightly under lunar gravity is powerful. For now, it is only an image. The reality could be far more severe. Until these questions are confronted through careful study, settlement remains an aspiration rather than a plan. There is also the problem of return. Once you arrive, how do you leave? Without the means to depart, a settlement can quickly transform from a bold frontier into a one-way confinement. Anyone who lands on another world must confront the unsettling question of how they would ever come back. On Earth, a launch site is supported by vast industries that provide liquid oxygen, refined fuels, tanks, and pumping systems. On Mars or the Moon, none of that infrastructure exists. To launch a return vehicle, settlers would either need to bring a fully fueled ascent rocket with them, a massive logistical burden, or manufacture fuel on site using unfamiliar resources under extreme conditions. For Mars, several approaches have been proposed, including using the thin atmosphere rich in carbon dioxide to produce methane and oxygen through chemical reactions. Space agencies and private companies have studied this carefully because it offers a potential path home. Yet while the chemistry is simple in theory, building machinery that can operate reliably at large scale for years without failure is extraordinarily complex. Even if such systems worked, the energy required to produce enough fuel for a return journey would be immense. Vast solar arrays or nuclear reactors might be needed, far more infrastructure than an early colony could realistically construct. On the Moon, there is no atmosphere to exploit, though ice may exist in permanently shadowed craters. The challenge there lies in mining ice in environments colder than anywhere on Earth, transporting it safely, and operating complex chemical facilities to convert it into usable fuel. Once again, this demands heavy machinery, skilled personnel, and continuous power. Until these methods are proven, the safest option would be to place return vehicles in advance, already stocked with fuel. The rocket itself presents another obstacle. Leaving Mars or the Moon still requires engines, tanks, and guidance systems. On Earth, rockets are built in enormous clean rooms, tested extensively, and repaired with new components when needed. On another world, a damaged valve or cracked engine nozzle could mean catastrophe, with no replacement available. For that reason, any return vehicle would need to arrive in perfect condition and remain stored, possibly for years, without degrading.